What's up, man? I have some in the back. Look under the trash can back there. Yeah. They have 8 each. Are you talking about on the first? Hold on. I'm trying to see if I can get this whole picture here, but I can't. Once you finish it, thank you. Once you finish it, it's 8. Okay, so let's talk about these individually. As you guys are going through these, so make sure you're correcting. Let's talk about geometry. Let's talk about polarity. Let's do the whole shebang, okay? So as you're going, you're noticing that you have 8 valence electrons. You have this ammonia molecule, NH3's name is just ammonia. You have this great lone pair up here. What geometry does it have? Molecular geometry. If you need a cheat sheet, you have a cheat sheet on your desk, but you can also try to imagine it based on how we did our yoga last week. Yeah. The first one, it's geometry. It's geometry. I wanted the shape, and then we're going to talk about polarity. Yeah. Right. So remember, we just had this big conversation about how molecular polarity deals with 2 different factors. The bond polarity, which we don't necessarily need to look at every single time, but I know we can do that if we need to. But also the geometry, and that's why I'm asking geometry first. Trigonal, pyramidal. So if you're a pyramid, you got a big lone pair on top. What's your partial charge on the top up here? What's the partial charge up here? Partial positive or partial negative? Not everybody at once. Yeah. It's even a lone pair of electrons, right? They carry negative charge. That should be a partial negative up here. And then down here, you have a lack of electrons. And so, Caroline, what's the polarity? Polar. So it's polar molecule. And that's because you have a partial negative and a partial positive due to the nature of how the geometry works, where you have a kind of a hemisphere that's partially negative and a hemisphere that's kind of partially positive. All right, if I'm a polar molecule, I only have 2 intermolecular forces I could have. What and what? Hydrogen bonding or dipole-dipole? Which one is it in this case? Why is it hydrogen bonding? It's not because hydrogen is there, though. It's very, very specific. Hydrogen has to be bonded to a very electronegative element, which is F, O, or N. N is this case. So I'm going to put HB here for hydrogen bonding. Good so far? All right, that's how you use that domino effect. Once you get one thing, you can get the rest of them. Next one, we have water. I think we know the geometry of this, but what's this geometry? Bent. Okay, if it's bent, those lone pairs, you know, we got nothing on them. They're very partially negative, and the hydrogens are very partially positive. So, is it polar or non-polar? Polar. Okay? If I'm polar, I have 2 options, dipole-dipole or hydrogen bonding. Which one? Because hydrogen's bonded to O. It's not because hydrogen's present, it's because it's very specific bond. It's a very specific bond. What's the shape of CF4? Shout it out. Tetrahedral. Okay, so really good distinction here. We have these 2 things that look like a square, right? On paper, they both look 2D, right? They look like a square. So whenever you have a tetrahedral structure, you have one that kind of has like a 3D shape like this, and their bond angles are 109.5 degrees. Do you remember that from your Vesper test? Okay, that's like a 3D shape. We did our did our yoga with that, but that's the one that's tetrahedral. Otherwise, if you have a square planar one, it actually is square. This is like a 3D square here, and so X, 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 and there's a huge lone pair here and a huge lone pair here. So the 2 lone pairs squished all the ligands in this flat square, versus being able to take on like this 3D structure like a trigonal or like a tetrahedron does. So when you're building those, you actually can see them a lot better. But yes, that is tetrahedral if, and this is where I actually do want you to look at the molecular polarity. Let's go ahead and check this out. Carbon and fluorine, what's their electronegativity differences? Carbon's a 2.5, and fluorine's a 4.0. So who's oversharing, who's overtaking the electrons from the bonded pair here? Fluorine, absolutely, for sure. I thought I could maybe, okay, whoa, that's really big. Let's go down a little bit. Where am I at? Fluorine, okay. So this dipole moment actually points from carbon to fluorine, from carbon to fluorine, from carbon to fluorine, from carbon to fluorine. So we can look at the lone pairs and we can look at the bond polarity. It's going basically north, south, east, west. So what would you say about the molecular polarity there? Because partial negative, partial negative, partial negative, partial negative. Do you see opposite ends anywhere? No. No opposite ends? nonpolar. Okay, if I have nonpolar bonds, what's my only option for IMF? London dispersion forces. Yeah, London dispersion forces. Okay. Now we have ionic, right? Yes.
What exactly do you mean by no opposite ends?
Meaning I don't have opposite charges present. Because I have a partial negative, because I have the electron lone pairs, and I have this like push towards the flooring of electronegativity. So I have partial negative in every position possible, and mine's getting crowded here, every position possible on my structure. So if they're all negative, there's no opposite ends. That's how you figure it out. Okay, so we've got this nonpolar and then London dispersion force. If I'm ionic, am I a molecule? No, ionics are not molecules. They have another name. It's called formula unit. We're gonna go over that later. But if I'm not a molecule, can I have intermolecular forces? Can I have molecular polarity? No, if I'm not a molecule. If it says molecule, it doesn't apply. So molecular polarity, just drop it right there now. Yeah. So this one is not going to have any polarity. So just put Na, and it's going to have a totally different way of determining its attraction. So we're going to get to that in a second. Next one, PCl3. What's its shape? Shout it out. Look at and if I need to keep reviewing that, I will, but look on your little cheat sheet in front of you, 3 ligands and 1 lone pair. Trigonal pyramidal. So I drew it a little differently than I drew the first trigonal pyramidal, because I wanted you to think about it. So we've got 3 legs, 1 lone pair. This one's trigonal pyramidal. Polar or nonpolar based on its geometry? Polar, likely, because that lone pair there, that offsets the geometry, allows it to have a very, very partial negative right here. And despite I know that there's lone pairs over here, I'm going to stick with generally a trigonal pyramidal with a lone pair on the central atom. Generally is going to be polar. Okay, so if that's polar, we have 2 IMFs we can choose from. What and what? Hydrogen bonding and dipole-dipole. Which one? Why dipole-dipole? There's no hydrogen bonded to FO or N, right? So dipole-dipole is our IMF. Next, this one's really easy. If you have a molecule that's got 2 dots or 2 atoms, and they have to be attached. They have to be attached with a straight line, right? Well, what's their geometry then? Linear. And so this one doesn't apply on your sheet because we don't have a central atom to really hone in on. So we got a linear structure. What's its geometry? I mean, molecular polarity. Because it's like same on both sides. No one's got more electrons than the other. Partial negative on both sides with those lone pairs. There's no opposite ends, so it's nonpolar. IMF. London dispersion forces, right. LDF, London dispersion forces, because a nonpolar has to have London dispersion. Okay, last one is ionic. And I didn't really go over that. Let me go back up real fast. We have this magnesium with 2 valence electrons in each, so there's 2 Cls, right? So I just drew them twice. Each Cl had 7 valence electrons, yes? So I drew one going to one lone electron going to one chlorine, the other going to the other chlorine. So both of these now have octet, and so that it's hard to see. My pen is so off. There we go. So magnesium lost 2 electrons. It has a 2+ charge. Each chlorine gained 1 electron. Each of them have 1 negative charge. So a 1 minus is a 1 negative charge. And then since there are 2 that I just popped a 2 out there, you could also draw it twice. Yeah.
So if we drew it like we drew the arrows, but those with the charges, would you just like it have to be brackets?
It has to be in the brackets because that's showing you the transfer is complete. Showing like these are now mine, kind of thing. And then now sodium chloride is the same story. 1 valence electron, 7 valence electrons. So I didn't actually even show the transfer here, but I showed the aftermath, which is sodium having a 1+ charge and chlorine having that octet, which means it gained 1 single electron. So it has a 1 negative charge. Yeah.
Well, you know what's ionic when you add it to 8? So it's like 7 + 1.
Not necessarily, because you can do that with a lot of them, right? How do I know something's ionic? Go back to the very first day. Jillian. Right, you always have to think about, is this a metal and non-metal? Yes, it is. And same thing with the magnesium chlorine. All right, so we can do that now, right? Now let's rank them. I haven't shown you the ionic thing yet. Let me go ahead and show you that first. And you're going to write this down elsewhere. I got to fix this. It's so huge. Okay. Oh my goodness. Let's just go to 100. Okay. So the only thing I did not talk to you on the video and your notes about was how do you determine the strength differences between 2 ionic structures? So you're writing down lattice energy. Where have you heard the word lattice before? The structure of an ionic compound is a 3D structure called a lattice. And a lattice structure is very, very difficult to break. Well, you got to have some relative comparisons though. So we have to talk about how one lattice structure, this one in particular is just sodium chloride and ACl, how is this lattice structure stronger or weaker than another lattice structure like its comrades, its other types of ionic compounds? So the way we determine it is we call it the charge product. So when I say depends on charge, what we have to do, and I don't know why this 3 is here, sorry, it's just aluminum oxide. What we have to do is we have to multiply ion charges. And whoever has the largest charge product, and why does that make sense for me to call this charge product? Because I'm multiplying, right? It's a mathematical product. You're multiplying charges. So whoever has the largest charge product wins, and that's the stronger of the ionic bonds. So everybody look for aluminum on your periodic table. Aluminum. Tell me the charge it would form, its ion it would form. And so the way you determine how many electrons it gains or loses is based on how close it is to octet, right? So look at aluminum and raise your hand when you think you know the charge it will form. You guys, everyone has a periodic table accessible to them. +3. All right, Jacob says +3. Does everybody agree? It has 3 valence electrons. It's going to drop off those 3. It gets a 3 charge. So I'm going to write just aluminum with a 3+ over it like this. Oxide is who? Oxygen. Look at oxygen. Find oxygen. And if I need to review that, I'll review it up here on the wall. You're looking for oxygen on the wall, and you see that it's really close to octet. It has 6 valence electrons. That is a true statement. However, how many electrons is it going to gain or lose? It's going to gain or lose? Gain. So 1, 2. So you're forward. Gain 2 electrons, which gives it a what charge? -2. What's 3 times 2? 6. Charge product. Ignore the charges themselves. Look at the magnitude, the number. Okay, so 3 times 2 is 6. Look for sodium. Let's do the same thing. What's the charge that sodium will form? So it's in group 1, right? So it's not going to gain 7. That would be like insane. It's going to lose 1 and back up to neutral gas. So it is now going to have a +1 charge. What about chlorine? Yes, it's going to have a -1 charge. How do you know that? Right, so 7 valence electrons, really close to 8, so you gain 1 electron. So 1 times 1 is? 1. Okay, sodium oxide. Well, we already did sodium, right? What's its charge? +1. What's oxygen's charge? We already did that one too. -2. What's 2 times 1? 2. So, who has the strongest ionic bond? Aluminum oxide. Who's next? Sodium oxide, and then next? Sodium chloride. Okay, so the reason I'm telling you that is because what we have to do now is rank them in accordance with boiling point, or rank them in accordance with how strong their bonds are. Well, ionic is 100% the winner chicken dinner, okay? It is 100% stronger than a covalent bond, just a single covalent bond. But then you have to talk about the 2 ionics together. That's what we have to learn how to rank them. I'll come back to this bottom section in a little bit. So, what you need to do, let me go back to my pictures. There. Okay. What we need to do is look at the 2 ionics. We're going to rank one of them number 1 boiling point, meaning the highest boiling point, strongest bond. We're going to rank the other one number 2 because it's the second highest boiling point or the second strongest bond. So looking at your 2 ionics, you got sodium chloride down here and magnesium chloride. Who is going to have a let's go ahead and do the charge product, and then I'll ask that again. What's the charge of magnesium? Look on the periodic table. So it's in the second group, so it's got 2 valence electrons. It backs up 2 because it loses those 2. So magnesium, I'm just going to put that right here, has a 2+ charge. What about chlorine? 1. So it's in the valence, it's in 7th group, it's going to gain 1 electron, -1. So what's that charge product? 2. Okay, sodium chloride. What's the charge? +1 for sodium and -1 for chlorine. So what's that charge product? 1. Okay. Who has the highest boiling point? Say it loud and proud. Magnesium chloride, because it has the stronger charged product, the higher charged product. So I'm going to just put like number 1 right here and circle it so that you guys know that this is the highest boiling point. Who's my second highest boiling point? Sodium chloride is my second highest boiling point because it has the second strongest ionic bond. All right, so thus far we've only talked about the strength of an ionic bond, right? Well, in your exploration, you talked about the strength of intermolecular forces, right? So we have ionic being the strongest. Who's the next strongest force? Hydrogen bonding, and then what? Hydrogen bonding, dipole, and London dispersion. Okay, so let's go ahead and rank those following. However, what if you have a tie? What if you have two that have hydrogen bonding? There's a caveat. Did anybody look to the bottom of the Google Doc where I put some extra notes? Say again? Darcy, did you say yeah or no? You looked them up. All right, well, that's even better. So, I'm going to show you this as well before I actually tell you that. It's good that you guys have a lot of background because then you actually, this all makes sense now. The first time you see this, sometimes you're like, what is this? But it's good that you've seen a lot of this before. So let me help you. Let me start from the bottom here. Hydrogen bonding. You got all of this taken care of. You know all this except for increases as molar mass increases. Molar mass. Well, what's mass? What's mass? Weight. It's related to the weight. And if you had to, look on the periodic table, could you find the weight of everything? Yeah, it's like right smack dab in your face, right? So if you're comparing two molecules that are hydrogen bonding, the way you figure out who has the stronger hydrogen bond kind of attraction, what you have to do is you have to add up their molar masses. The heavier one wins. So molar mass is just periodic table masses, and we would add them together in accordance with whatever the molecule says it's consisting of. So go back to your chart. So we're working from that chart still. Which two had hydrogen bonding? So I heard NH3 and NH3 versus water. It's like Batman versus Superman here, guys, okay? So this half the room, tell me the molar mass of NH3. This half the room, tell me the molar mass of H2O. Look at your periodic table. Not the one in front of you because that one doesn't have masses on it. Look at your like true periodic table. So you're going to look at them and add them up. The masses. Yeah, you take a look at the one that Maddie's looking at. So this one doesn't have masses. All right, this half the room, tell me NH3's mass. Approximately 17 grams per mole is how we're going to say that. 17 grams per mole. And I'll tell you about molar stuff later, but grams per mole is how we denote that. Nick, y'all's group, so tell me here what's water's mass? Total. Approximately, so 16 plus 1 plus 1, yep. So that's 18 grams per mole. That's mole. Okay. Ooh. Okay, so 17 versus 18. Who gets the higher force? H2O. Okay, so I'm going back to the chart. You guys with me? I'm going back and forth to this chart quite a bit here. Okie dokie. So number 1 was the strongest ionic bond. Number 2 is the second strongest ionic bond. Now we're in covalent land. In covalent land, we have to look at bonding forces. So water would be number 3. It's the third highest boiling point. Who's number 4? NH3 is the fourth highest, and we did that based on what? Molar masses, or masses, right. All right, so after we've gone through ionic, hydrogen bonding, we have dipole, that's next. How many of these were dipole? Just one. Do we need to look at masses or anything? Nope. If I did have, and I'll tell you it's the same thing, if I did have things that were tying, like meaning both multiples that were dipole attraction, we would do the same thing as we did with hydrogen bonding. We would look at masses. So what number is PCl3 in boiling point? So it's the 5th highest boiling point. Okay. Yes, Chloe.
So if it's ionic, it's not going to have a
Right, and that's a good point. So the words that we say molecular polarity or intermolecular forces, those are for molecules only. And when I say molecules, you're thinking covalent. Never do we talk about ions in that manner. Okay, so let's go back to the last one. And this is So this is the same thing I told you, dipole. Again, if you're comparing just like or hydrogen bonding, it's the molar mass differential that helps you determine the differences between them. This is the one for London dispersion force. I'll let you write down the brief on how do you determine whose force is larger based on number of electrons. This is nice. It's all over on that paper right in front of you. It's all together. So if you have a situation, which we do now, where we have two or more London dispersion forces, and you're like, okay, how do I figure out which London dispersion force is stronger? You actually consider number of electrons, and the logic behind that is because the London dispersion forces don't work based on their masses. Their attraction occurs because of shifting of electrons. So look back at your chart and tell me who has London dispersion forces. Look back at your chart. Caroline.
CF4.
CF4 and N2. Is there anything else? That's it, right? Okay, number of electrons. So there's two ways we can look at this. We can look at the number of electrons on the structure, or we can count the valence electrons. Let's do both. Look at the number of dots on the structure. How many dots are on CF4? Dots? Dots? So 6, yeah, 24. Okay, so there's 24 that are just dots, right? And I'm just gonna put dots right there. How many are dots, meaning like the ones that are on the outside for nitrogen? 4. Okay, so far, CF4 wins, right? Let's also do that just on the number of electrons that they have in terms of their valence electrons. This is what you would have done before we even drew the structure. That's the very, very first step in drawing your structures, right? The V. Count your valence electrons. This is what you guys were telling me. How many for CF4? 32 valence electrons and 10. Okay, so in both ways you count them. If you count just the dots, or you look at your first number you wrote down when you're drawing your loose dot models, 32 valence electrons, 1 second, Nick, can do more shifting. They can shift their little places, locations, and that causes this London dispersion force to be stronger. Because they do more, they can have more movement, or they have more effect on the charge than this one does. Question?
Yeah, what if they're equal?
They're equal, then we would have to go with mass. It's like our third tier of defense here. But hopefully you won't have to deal with that. Okay? Okay, so who's going to be number 6? Are we in 6 now? Who's number 6? CF4. Number 6, and who's the one that has the absolute lowest boiling point out of all of them? N2. Where would you find N2 in the world? This is number 7, by the way. Where would you find nitrogen gas? In the atmosphere. Have you ever seen liquid nitrogen? Have you heard of liquid nitrogen? Okay, some of us, it's like up in the college, university level labs. It's like it's really expensive. They have to have it under a lot of pressure, and they have a very, very cold system there. So nitrogen's boiling point is like, I don't know, -20, -200, something. It's a very, 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 very low boiling point because you never ever see it boil. It's always a gas, right? So liquid nitrogen's hard to get. You've never seen solid nitrogen? Probably none of us, because it's got to be under so much pressure, and it's got to be so cold. Because this molecule of nitrogen and this molecule of nitrogen, they're like, we don't attract. Like, we don't really have a strong force of attraction with each other. So much less are we going to, like, naturally stick together. You really got to push us together to make us liquid, and even push us further to make us solid. Because they don't like each other. I mean, they're both nonpolar. They both have London dispersion forces, which is the weakest of all forces. So they're just like, oh, you want to go gas? Oh, we go to gas. Because they don't really care to be next to each other like all these other things do. Question? It deals with the fact that it's diatomic makes it nonpolar. Because they both have equal share of electrons. They're like, we're not going to take them. I'm not going to take them either. So let's just share, and then there's a nonpolar molecule for every single diatomic molecule out there. Okay, I'm going to pause for a moment. So I think I've explained a lot of the physical properties. We went over that pretty in depth. You guys feel okay about that? If you had to rank them, you can rank them in this order. And with your differentials like weights and electrons. Okay, so here's what I like to do. We have about 45 minutes left. You guys have molecules to build, and me, I'm going to be running around like a chicken with my head cut off to come and check them. You guys also have your problem set 7-8. So after you build your molecules and you're like, Miss Inlow's not going to get to me because she's struggling with this other group, take pictures of them. Like, line them up and take pictures of them. If you have pictures, I will check your pictures. That way you don't have to build them again. But I'm going to let you guys work on both things right now. The modeling kits are right here behind Audrey. We also have problem set 7-8 you'll be working on. And I'll kind of pull us back towards the last 5 minutes of class. But you got time to work. Let's get this baby done.